All right, here we're looking at section 10.5. So our learning targets for this section are to use the formula for the number of permutations. Then we're going to use the formula for the number of combinations, and we're really going to figure out the difference between these two things. And then we're going to be using combinations in the binomial theorem to expand some binomials. So the first thing is a permutation is an arrangement of objects in which order is important. So for example, here's our different permutations of A, B, and C. So you'll see that I have all three letters in here all the time, but the order is different. So that is a permutation, is my order is important. So now I want to look at this first example. So we want to consider the number of permutations in the letters of the word July. In how many ways can you arrange A, all of the letters, and then B, two of the letters? So we're going to use our counting principle to find the number of permutations in the word July. So I have to look at my number of permutations as the choices for the first letter times the choices for my second letter times the choices for my third letter times the choices for my fourth letter. So I'll see that I have 4 choices for my first letter because I can pick any one of those 4 letters. Then I only have 3 left. Then after I pick that second letter, then I have 2 choices left, and then I have 1. So then I multiply all of these together and end up with my permutations of 24. So there's 24 different ways that I can arrange the letters in the word July. So now let's look at part B. When arranging 2 of the letters of the word July, I have 4 choices for the first one and 3 choices for the second one, and that's it. I don't care about the rest of it. So now I just multiply that 4 times 3. And there are 12 different ways that I can arrange 2 of the letters in the word July. So here's your first monitoring progress. Try them and see what you can come up with. So here's what we kind of looked at. In that first example, we evaluated 4 times 3 times 2 times 1. So this is written as 4 with an exclamation point. So that exclamation point is called our factorial. So here's what this means. So any positive number, the product of integers from 1 to that number is called a factorial. So if I take that number and I multiply it by everything below it, all the way to 1, that's called a factorial. So just to keep in mind when we're dealing with factorials, the value of 0 factorial is going to be 1. So that just helps us. So in example 1b, I found the permutations of 4 objects at 2 at a time. I can still use kind of some factorials, but I have to use a couple of other things, including this formula. So here's our permutation formula. So the number of permutations is given by this p we see in our calculator a lot. That's permutation, and n factorial. Right, so the number of permutations of 4 objects, which we saw in this first example, was just 4. If you're typing it into your calculator, you're going to type in 4, and then go over to permutations, and then 4, and it'll do this 4 factorial for you, and come up with S. So if I'm taking different numbers of things, right, so here in this top example, I was taking all 4 objects and looking at all 4 objects. Down below, I'm not, so I'm taking 2 different objects, which we saw in part B of that first example. So I'm going to have my n factorial on top, divided by my n minus r factorial on the bottom. So let's look at our calculator. So our example for here was we had 4, and then to find that in your TI calculator, you can hit math, and then you'll see if you go over to probability, you'll see here's a permutation and combination, but we're looking at permutations, and I'm looking at 2. So then I see I have 12 different possibilities, which is what we saw before too, as well. So my calculator can help me with this. Or if I don't have a calculator, I can do it by hand. So I have 4 factorial divided by 4 minus 2 factorial, which ends up being 12. So now let's look at an example of this. So 10 horses are running in a race. In how many different ways can the horses finish first, second, and third? Assume there are no ties. So the first thing I notice is they finish in different places. So that tells me that I am looking at a permutation rather than a combination, because order here matters. Okay, so I have to find the permutations of 3 horses chosen from 10. So if I have my calculator, I can put in 10p3, or I can use my permutations formula. So I take the total that I start with, and then I take on the denominator, I'm going to have 10 minus how many I'm picking, and factorial. So I end up with 10 factorial divided by 7 factorial. So this also means I'm going to factor out and expand my factorial in the numerator, and divide out my common factor, which is 7 factorial, and then I can simplify. So really I have 10 times 9 times 8, which gives me 720. So there are 720 ways for the horses to finish first, second, and third out of those 10 that we started with. So now here's our next example. For a town parade, you will ride on a float with your soccer team. There are 12 floats in the parade and their order is chosen at random. Find the probability that your float is first float with the school chorus is the second. So again, kind of order matters, right? We want to be first and school chorus second. So I write the number of possible outcomes. So there are 12 floats in the parade, so I know that that's my total. So then the second part is I'm going to write the number of favorable outcomes is the permutations of the other floats, given that the soccer team is first and the chorus is second. So this is going to be my 10 factorial. So now I just have to find my probability. So the probability that the soccer team is first and the chorus is second is 10 factorial divided by 12 factorial, which I can then factor out and simplify. So 1 over 1 divided by 132 is my probability that the soccer team is first and the chorus is second if these floats are assigned at random. Okay, so here's your next monitoring progress. Try it, see how you do. So now we're looking at combinations. So a combination is different than a permutation because order here doesn't matter. So the example that they give, for instance, in a drawing for 3 identical prizes, you would use combinations because it doesn't matter if you're picked first, second, or third, you still get the same prize. So now let's look at this example. So count the possible combination of 2 letters chosen from the list A, B, C, and D. So first I want to list all of my permutations, and then I cross out my duplicate pairs. So if I start with A, I can have A, B, I can have A, C, I can have A, D. Then if I start with B, I do the same thing. C and D, I do the same thing. So now that I have that, I can cross out my duplicate pairs because BD and DB are the same thing. And then I figure out that there are 6 left over that I haven't crossed out. So that is my 6 possible combinations of my 2 letters from that list. So here's your next monitoring progress. See how you do. So now here's my formula for combinations, right? And remember, a combination order is not important. So the number of combinations is given by I have my n factorial, which is the total number of things that I have, and then I've got n minus r factorial times r factorial. And I have to do this subtraction first, remember. So here's from this last example, the number of combinations of 4 objects taken 2 at a time. So I've got 4 factorial in the numerator, 4 minus 2 factorial times 2 factorial in the denominator, and then I can simplify and find my answer that way as well. So let's look at this example. You order a sandwich at a restaurant. You can choose 2 side dishes from a list of 8. How many combinations of side dishes are possible? Often we're not told if it's going to be a combination or a permutation, so we have to figure that part out. So here I would know it's a combination because it doesn't matter which side dish I pick first, I still get to eat them. So again, here my order is not important, so I want to find the combination of 8 side dishes taken 2 at a time. So I use my combinations formula and I just plug in my n and my r. And remember that n is always the total number of things that we start with, and r is the thing, how many you're picking or how many you're taking. So I go ahead and use my formula, then I subtract my 8 minus 2. I expand my factorials and divide out, and then I can multiply and simplify. So I know that there are 28 different combinations of side dishes that I can order if I take 2 at a time out of the 8 total. So here's our next example. A yearbook editor has selected 14 photos, including one of you and one of your friend, to use in a collage for the yearbook. The photos are placed at random. There is room for 2 photos at the top of the page. What is the probability that your photo and your friend's photo are the 2 placed at the top of the page? So again here, I just think the order is not important because I just know that 2 are being chosen to be at the top. It doesn't matter which one's first or which one comes second, they both get to be at the top of the page. So that tells me that this is a combination. So I want to write the number of possible outcomes is the number of combinations of 14 photos taken 2 at a time, right? Because there's 2 possible that I'm taking and there's 14 total because the order is not important. So I use my combinations formula and I subtract, I expand out, and then I simplify. So there's 91 here. So then I want to find the number of favorable outcomes. So only one of these possible combinations includes my photo and my friend's photo. So I now have to find the probability. So the probability that both of our photos are chosen is going to be 1 divided by 91. So first I just have to find out how many total possibilities are there, and then I know that there's only one of those possibilities where both of our pictures are at the top, so then I can find the probability from there. So now here's your next monitoring progress. Try these, see how you do. So now we're going to be using the binomial theorem. So the binomial theorem is a way that we can expand some binomials without having to do all the multiplication. So the big thing I have to notice is I have a plus b in here. I always have to make sure I have a plus in between my two terms in my binomial. Now this is a lot of letters and a lot of numbers, so we're going to look at some examples of this. So I have a plus b to the n. So here, when I'm using the binomial theorem, I'm going to be using combinations. And I always want to start, you'll see here, I take a combination with n out of n terms, and I pick 0 at a time. And then my a value gets the exponent of n, and my b value gets the exponent of 0. And then you'll see as I go up each term, the exponent for my a decreases and the exponent for my b increases each single time. So then I also know that each term in this expansion, right, because I'm expanding it, making it a full in standard form, has the form of I take my combination of n terms r at a time of a, so there's my a, n minus r, and then b has the exponent of r. So let's look at an example of this. So first I want to use the binomial theorem to write out this expansion. So I could really just multiply all this out and then put it in standard form in the correct order, and I would have that, but that will take a long time. So that's what the binomial theorem is for. So I just rewrite everything. First, I make sure that this is a plus in between. I see I have an n of 3, so I find my 3, my combinations, and I rewrite everything with my exponents. So you'll see here my a, my first term in here, has the exponent of my n, and my b has the exponent of 0, and then my a exponent decreases by 1 each time. So I start with 3, then 2, then 1, then 0, and here it goes up by 1. So 0, 1, 2, 3. So now I can find these combinations. Oh, and my calculator died. So all of these numbers, let me just underline them. These numbers right here are found by using your combinations. These are your combinations, right? And so we just can put these into our calculator and find those values. So then from there I just simplified my exponents. We know that anything to the 0 is 1, so that's where these extra ones come from. So I just look at each piece and simplify it, finding my combinations, and then I can simplify each term. So this ends up just being x to the 6th plus 3x to the 4th y to the 1st plus 3x squared y squared plus y to the 3rd. So you see that it's already in standard form for us. So now in part B, using my binomial theorem, I know all of my pieces, and I could write them all out, and that would just take forever. Because what I'm asked to do is I'm asked to find the coefficient of x to the 4th in this expansion. So I know that each term in the expansion, and this comes from that last, that core concept. So if I have 10 objects, right, because I'm told I have 10, I take my combination of r, my 3x to the 10 minus r, and 2 to the r. The term containing x to the 4th occurs when r equals 6. So x to the 4th, right? I know that I'm trying to get an x to the 4th here, and I know that 10 minus 6 will give me 4. So then I can put that in and simplify and solve. So I know that I would take my combination of 10 items, taking 6 at a time, put that in your calculator, 3x to the 4th and 2 to the 6th. So then I can use this, and I just use my calculator and solve that. So the coefficient, right, is just that number that I get here. This one's kind of tricky, so spend a little bit of time working through this. See if you can find a different term in this same expansion. So now here's some monitoring progress. Really try this number 9 and 10 to see how you feel with the binomial theorem. And again, with this binomial theorem, we're always just going to be using our combinations. So now let's look back at our learning targets. So first we had to use the formula for the number of permutations. which we have done that, and we realize that permutations are something where order matters, right? This is where we have something first, second, third. We want to put things in different order on our bookshelf, those kinds of things. Order matters for this permutation. Then we looked at the formula for the number of combinations, and here the combination, the order doesn't matter. Then we were able to use combinations in the binomial theorem to expand binomials and find certain terms. So now that we've tried this, go ahead and work on your homework for 10.5.